Assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. So I hope you all had a wonderful Thanksgiving and have all recovered from your various food comas that you might have been put into. I know I sure have, and I did want to get this episode out actually before Thanksgiving, but work kind of got busy and then Thanksgiving kind of happened and there wasn't really any time, but here we are a week late, but that's okay. But this episode, long before artificial intelligence or AI, the latest AI hype cycle started freaking people out and AI becoming a massive buzzword and all the buzzwords surrounding it and it basically being shoved down everyone's throats and trying to solve problems that don't actually exist. Personal recommendations were one of the OG technologies that really freaked everyone out. And to be honest, it still kind of does freak everyone out even today. I mean, how many times have you been scrolling through your social media feed or, browsing on your e-commerce website of choice when you see something that looks eerily similar to something that you were thinking about or maybe wanting to buy, and bada bing, bada boom, there it is. It turns out that these recommendation systems are actually kind of dumb, and there's a very almost certain chance that these systems actually have absolutely no idea what it's actually recommending you. It's like artificial intelligence in that sense, where it has absolutely no idea what it's talking about. It's just running a math calculation to figure out what the most probable next word's going to be and spitting that out to you. But in this case, it's actually deterministic, and you can actually know for a fact what it's going to recommend you based on certain inputs, which is honestly, in my opinion, a much better design because not only is it very smart, but it also is easily testable. You don't have to worry about it randomly making stuff up, unless, of course, you throw in some randomness into there, which, of course, you absolutely could do. There's a lot of weighting type systems that go into these recommendation algorithms, so you could have a weight in there to just throw in a random recommendation in there, which might not land. Maybe it does, maybe it doesn't. But aside from that, you can pretty much guarantee what it's going to recommend you, assuming you know what the weights are. You can account for that in your testing, which makes it a lot easier to test and verify rather than, current large language models. But in this episode, I kind of wanted to, go into how these recommendation algorithms work, and show you how they actually work, because when you really understand under the hood what they're doing, it kind of removes a little bit of that shock factor, and it's like, oh, it's just looking at numbers. Okay, cool. It's not actually that impressive. The emperor is in fact wearing no clothes. So that is what we're going to get into this episode. But first, let's start off with our trivia question for the week. So, in the spirit of recommendation algorithms, Aline Rich was credited with creating the first recommender system called Grundy. But what year was Grundy created? So, what year was Grundy created? Which, if this gives you a hint, it's probably earlier than what you're thinking right now. But with that, let's get into this week's cybersecurity tip. So this week's cybersecurity tip is always to make sure you are mindful of current and emerging cybersecurity threats. Now, we talk a lot on this podcast about how cybersecurity is essentially a never-ending arms race. As soon as a threat actor creates a vulnerability or an exploit, the good guys go ahead and patch that exploit, and then the attackers find another one, and it just keeps going, and going. Now, some of the tricks have been in use for ages, things like buffer overflows and other types of memory exploits. Those have been around for a long time, but as new technologies come out, new means of exploiting and attacking and various attack vectors have been created. So, before email was a thing, there was no like spear phishing attacks through email or phishing attacks through email. But then as email kind of became a technology, that was a tool that attackers tried to use. And as new technologies come out, it's almost a guarantee that at some point in the existence of that technology, some sort of exploit or attack will be used against it to try to do something, whether that's gain unauthorized access to, I don't know, get privileges on I don't know. I mean, what does an attacker exploit for? You trying to get information from a government, a rival company, um, some other government, foreign entity. I mean, the list kind of goes on and on. Um, so it was really only a matter of time before AI would be involved in some sort of serious cybercrime. And back in November, that's basically exactly what happened. So Anthropic has an article out, which I will have linked, which is kind of the inspiration and everything for this cybersecurity tip. So all of this information is in that article if you want to go check it out. But essentially, back in November, the first reported AI orchestrated cyber espionage attack took place. Now, it took place against the usual suspects. And what do I mean by the usual suspects? Well, large tech companies, financial institutions, chemical manufacturing companies, and government agencies. Government agencies being the big one because everyone tries to target government agencies and large tech companies for that matter. So, in the world of agentic AI, which is kind of one of the latest buzzwords out there, which for all of you out there in English, essentially what that means is it's an AI that can perform actions on your behalf without you physically or actually telling it to do stuff. So if you think of your current large language models, you can ask it questions and then it'll try to answer that based on what's in its kind of knowledge base, if you will. But the kind of the appeal, or I guess the hype of agentic AI, is essentially to allow it to use different tools through various protocols to allow it to do more than what's just in its knowledge base. So, do things like search the web, use other online tools, run commands, create files, edit files, the list kind of goes on and on. It can perform actions on your behalf. So, in this case, what happened was the threat actors convinced Claude to perform small but seemingly innocent tasks, so Claude would execute them and essentially bypass the guardrails that exist on Claude. Now, if you're not aware, pretty much any kind of AI that's publicly available has guardrails in place to prevent it from going completely unhinged. Now, there are ways and documented ways that you can get around these guardrails, or if you kind of run the models locally, they almost never have the guardrails on in the first place. But in production environments that are available to the public, they almost always do. So that's kind of always step one when you're trying to get one of these AI models to do something it's not designed to, is how do you get it to bypass its various checks and guardrails in order to make it do something that it's not intended to. So that was kind of what their first step was. So by performing, small tasks that seem kind of innocent and not really giving it the full context, it's not necessarily able to clue in on what it's actually doing. But the other thing that they told it was that it was part of a cybersecurity firm, and it was the tasks it was going to be performing was for defense testing in order to, again, further try to fool it into performing the malicious actions that they want it to. So, which actually is kind of smart because if you're a pen tester, that's essentially your entire job. Because if you're a pen tester, you're literally being hired to perform malicious actions against a company or an organization in order to gain unauthorized access, exploit systems, and do other things that you're not supposed to. But at the same time, you have been given permission by the organization that hired you to do all of those things, so it is not illegal because you have authority to do it, which is essentially what they tricked the AI into thinking it was in order for it to actually go ahead and perform these actions. So in this case, um, Claude was told to perform first. It was told to perform reconnaissance of the organization's systems and infrastructure, which kind of makes sense. If you're gonna go and hack someone, if you're a pen tester, that's basically always step one. You gather as much information as you can, figure out, who your targets are, what their infrastructure is like, identify some potential vulnerabilities before you actually go trying to hack things. Because if you can identify, what their infrastructure is, what kind of services they're running, that can help you pin down potential vulnerabilities and exploits you can perform in order to, do your job as a pen tester, or in this case, as a threat actor, I guess. So since it's an AI, it's able to perform a lot of this reconnaissance a lot faster than any human could. Now, there are tools out there for us humans that we can do to, scan infrastructure, like Nmap, for instance, that can scan infrastructure to figure out, different services are running on different systems and things like that. But as an AI, it's able to kind of run all these tools a lot quicker, analyze it, and figure out what's going on a lot quicker than your typical human could. Um, so it's not really that far fetched that the AI would be fooled into being able to perform this task because, like I kind of mentioned, if you're a pen tester, discovering a vulnerability is kind of part of your job. If you're a hired pen tester to search for vulnerabilities, document them, expose them, and all that stuff, that's kind of basically what your job is. And obviously, step one is going to be performing this kind of reconnaissance. Um, and but after that, the AI was told to then create exploits in order to exploit the various vulnerabilities that it found, which again is not far fetched given the context that it's working in. Because if you think about it, if you're under the mindset that you are in a cybersecurity firm and you are trying to perform a pen test, that is kind of your job. If you find a vulnerability, part of your job, and if you even look at the open source community, people create proof of concepts for a reason. The reason you create a proof of concept is to basically show how this vulnerability works, so the company or organization or whoever is tasked with fixing it has something that they know will exploit them, which they can then create patches for in order to, not be hacked anymore. So creating a proof of concept is all part of that's all part of the job, except in this case, the proof of concept was used a little bit more than a proof of concept, and was actually used for malicious reasons. Because part of the process of, you know, documenting vulnerabilities and reporting vulnerabilities is kind of showing and disclosing how you manage to exploit the system, and showing that, yes, I use this exploit, which is usually a proof of concept, to then, infiltrate your system, and then maybe you exfiltrate some kind of data to show that you were actually in the system, to kind of prove that, yes, this exploit got me in, and here is what I found by just, getting in. Now, obviously, if you're a pen tester, that's basically where you're going to stop. You're just going to kind of get in, show the fact that you got in, and then after that, I mean, theoretically, you could do whatever the heck you wanted, but your job as a pen tester is basically done at that point. But after Claude created these proof of concept exploits and exploited things, according to the article, Claude harvested credentials that allowed it to further access and then extract large amounts of private data, which it then categorized according to intelligence value, and then it then identified high privileged accounts and created backdoors to exfiltrate even more data from said accounts with minimal supervision required. Now, the whole backdoor thing kind of sounds scary and everything, but if you think about it, if you manage to harvest credentials from a system, you're already on the system. So it's not all that difficult to think of adding some kind of mechanism to silently exfiltrate data off that system. um, in order to, harvest all the data that you wanted to. Because, like I said, you already have access to the system with the credentials. It's not like you have to perform some fancy exploit in order to, say bypass SSH or something like that. You literally have the keys to the kingdom with the username and password and the credentials. So if you think about it though, the whole like cover that the AI was given, I know I keep coming back to this, but it's so genius because it's literally doing everything that a pen tester would. Because at the end of it, they even mentioned in the article that it wrote up a documentation documenting, how it exploited everything and verifying proof of the exploit, showing the credentials and everything that it gathered. And that's basically, like I said, exactly what a pen tester would do when they would be generating a report for the organization that they were tasked with pen testing. Everything that I just described the AI doing is exactly what a pen tester would do. Except the difference is the AI did not have permission to do this, whereas a pen tester would. And remember, like I said, whenever I talk about pen testers, if you're ever wanting to get into pen testing, you always, always, always need to make sure that you have permission to do whatever you're trying to do, and you have your get out of jail free card, aka the letter from whoever hired you to do the pen test saying that you're supposed to be doing this, and if they have any questions, to call them and they can vouch for you. Otherwise, you can get into some very hot water. Um, but yeah, so like I said, this is like everything in cybersecurity. It's a never-ending arms race. Honestly, I'm kind of surprised it took this long for an exploit by entirely done basically by AI to happen. Now, that's not to say that AI hasn't been used in the past couple years to say write malware, for instance. I'm pretty sure that that's probably happened because it's not exactly that hard to do to ask AI to write some code for you that might be malicious. But this is really the first documented case where an artificial intelligence system was basically all on its own performing this exploit stuff. So like I said, it was pretty much just a matter of time. But now the ball is in the court of the good guys to figure out how the heck do we defend against this. But one thing I do find funny before we wrap up here with the cybersecurity segment is the article pointed out that Claude, quote, occasionally hallucinated credentials or claimed to have extracted secret information that was in fact publicly available. Which, I mean, if that doesn't sum up the state of AI, I'm not exactly sure what does, because the number of times that AI just blatantly makes things up or is just blatantly wrong is kind of hilarious. Now, if you're not in tune with, what you're asking the AI, or if you're asking it something very, very generalized, you're not going to notice this. But once you really get down into the weeds, it becomes very apparent that AI is actually not as smart as a lot of these companies and everyone trying to shove it down our throats would lead you to believe, which is also why I also find it very hilarious that even though these AI systems have been out for years now, basically every single one of them still has beta next to it. Like if you notice like any AI systems that you find on websites or basically anywhere, if it's an AI system, it almost always says beta or something about it being in beta, because then the company has essentially a blank check to say, well, it's in beta, so because it gave you wrong information and it's just because it's in beta, we're still testing things. I mean, I get that, but you're also essentially pushing it like it's a production service as well. So I don't know exactly how long the whole it's still in beta is gonna fly, because you have to understand that beta testing is actually a serious thing, but you generally don't want to beta test on the entire populace that uses your service. That's usually not good software development practice. You generally beta test on a small subsect of people, gather their feedback, make updates and whatnot. Or you can even do things like feature flagging, where you deploy, whatever your new changes is to a small select group of people. get some metrics on what they're using, how they're using it, how they're liking it, and then based on that feedback, you either can then just kill it right then and there, make tweaks as needed, or increase the number of people you push it out to until everyone gets the feature. But keeping it basically in beta indefinitely is, I mean, I don't think it's necessarily the best not cybersecurity, software development practice, but I guess what do I know? But yeah, that's basically gonna do it for this portion of the cybersecurity tip. AI is gonna AI, it's gonna make stuff up, and it is kind of funny that they were keen to call that out in the report. So, like I said, the article for this is all linked in the description below if you care to dive deeper into it as well. So, with that, let's get into what nerdy stuff have I been up to this week. So, this week I got back into some Pokemon programming, the video game I'm trying to make from scratch, all in C. It's been a hot minute since I touched this game, and that was very evident, as we will soon see. But for starters, I continued the whole refactor process that I've been working on, or where I left off with, I guess I should say, where I noticed that I was creating certain grids. So, like grids for interaction menus. So, for instance, if you've ever played a Pokemon game before, specifically the older games, like on the Game Boy Color, Game Boy Advance, you'll know that when you're selecting which move you want, there's kind of a grid of like 4 elements, 2 by 2, and then the same thing with the moves, it's 2 by 2. And then if you go into like your item selector, specifically in like Gen 3 era, if you select an item, there's also another like 2 by 2 grid. And I was noticing that every single time I needed to make one of these grids, I was writing all the code to do it, which is very bad computer science practice. So I decided to rectify the situation and create a function specifically designed to handle all of this for me. So in previous episodes, I talked about how I managed to get all that functionality working, and it was now a matter of changing the current implementations over to this new one where I just call the function and it does everything for me. And it's been pretty good, but there, of course, have been various other components that need changing because, like any time you do a refactor, it's usually a rabbit hole because you start pulling a thread and that pulls out something else, and then whenever I try to, it's like the whole let me implement this feature real quick. One of the most infamous words in software development, because you are not going to implement that feature real quick and you should stop lying to yourself. Because what happens is you start on this little feature like, this probably won't take too much time. You start working on it, you go to implement it somewhere, and you're like, oh yeah, I need to add this. And then you go add that. Well, in order to make that work, I have to go change this. And in order to change this, I also have to change that because that's a dependency of this. And it quickly spirals out of control to this quick feature you are going to implement real quick in about maybe 20 minutes, ends up being an all-day affair, if not more. So I got to the point where I had already done one of the menus, that being like the save screen, where there was actually no interaction with it. It was just displaying a multi-columned, selection option. So that was like the first thing I did, in order to just show that this function that I wrote can actually handle it. But the selection menus in the battle screen and the bag screen are a little more complex because you not only have to display the items themselves, but you also have to display the selection arrow and have the logic in place to be able to know what you're currently selecting. So that kind of is where the whole spiraling into having to change a bunch of different things kind of crept in, because it wasn't as simple as removing the display code to display the items and inserting the new one, because then you have to account for the logic of moving the arrow around and selecting things. So I did manage to get all of that cleaned up, and the nice thing about it was, because I already had this function and this struct to encapsulate all the data that I needed to actually display everything, I was able to remove a few variables from the battle screen, which was nice because I was able to remove code, which is always a good thing. And it also just made the code cleaner in general because there was a lot less redundancy. Everything was kind of encapsulated in objects. It was a lot more readable that way. There was a lot less one-off things for tracking things. So much cleaner, a lot nicer. And it was definitely very well done. Now, I only got the chance to do one of the move boxes. Like I said, it kind of took some time to get it working because adding the arrow selector in there kind of added another layer to things because if an arrow's in there, it kind of like you have to offset how the text is displayed to account for the arrow. So there was additional tweaking that I had to kind of incorporate into how the grid of items, in this case the 2x2 grid, is displayed, and also not break the other implementation, that being the save box menu. So there was some kind of tweaking and back and forth that I had to do. Um, and what I did, one thing that I was actually pretty proud of, with this kind of implementation of doing the selection error, was I wrote some custom logic in order to parse the integer position, in order to convert it to a grid position. Because how the logic currently generally works is in almost every single menu in a Pokemon game, you have a single list of items that you can choose from. The problem is, if you're in a grid, not everything is in order. So, how do you define the order? Well, basically, how the logic essentially worked was you take the current column you're in plus the total number of columns, and then you compare the remainder, and essentially by dividing in if there's a number afterwards. And if there's a remainder, your selection is not in that column because otherwise it would come out even. So it was an easy way to figure out which column I'm in. And then once you figure out which column you're in, you can just do some other math, actually doing the division to figure out which row you're in, and then basically by that you take a single counting number, so say 1 through 9, or I guess in this case 0 to 3, and then depending on what that number is, you can do those couple math operations and figure out which spot in the grid you're actually in. So I was pretty happy about that. It took me a little bit to kind of mentally think about it, and I did write some tests for it because I was like, wait, I think I got it, but I need to make sure. So I wrote just, some quick, simple tests, in order to just make sure to sanity check myself, to make sure that everything was kind of working as it was intended. But it's those kinds of small wins like that that kind of really make you love programming computer science, because you're tasked with this challenging problem of, okay, I have a list of items and it's a single number, but I need to convert that into a grid. How do I translate this into an actual grid given these parameters? And being able to do that on in a sense, and the nice thing about this solution is it's not just for a 2x2 grid. Because of how the logic actually works, you could set this grid to be 4x3, 10x11, 5x17, whatever you want, and the logic will still work and apply and work just the same, which is always fantastic when you can get one of those kinds of perfect universal solutions. And I love that. I think one of the other implementations I can think off the top of my head was I did a similar kind of complex universal logic, which actually wasn't all that complex, but basically to take what type the Pokemon is, to whatever like that type value coming into the function, and do some math to figure out where in the sprite sheet that type actually is in order to display it without having to like manually calculate everything. It's just a universal calculation that gets you the exact coordinates in the sprite sheet and displays it perfectly. Fantastic. Love when you get those kinds of wins like that. But here is where things start to get interesting, because that was actually the writing code portion, but we are maybe halfway through this segment because there is a whole bunch of infrastructure stuff that went horribly wrong. Because As you know, as I've mentioned on the podcast before, I have a CI/CD pipeline, or a continuous integration, continuous deployment pipeline. So whenever I push code changes to my uh, GitLab server that I host in my home lab, it automatically performs a series of things. First, it checks to make sure the code's formatted correctly. It then builds the code, make sure it actually builds properly. It then tests the code by running the automated test cases. So, and assuming it passes all of that stuff, then it goes through and builds the Doxygen documentation so I can actually have a fully completed documentation that I can refer to. And then it publishes that to a server that I host in my house, where I can view all the documentation from a web browser. It also has a PDF attached there as well, so I could download it if I wanted it to. So all of this, oh, I guess the other thing I forgot to mention, during the unit test phase, there's also another test in there to check for a basic, very dumb check to check for security vulnerabilities. Um, but all of that aside, it managed to get uh, everywhere except once it started trying to do the whole Doxygen documentation creating. So once I pushed the code to the pipeline, let's just say I had to break out the plunger in order to unclog this pipeline. So basically, what first started, so the first issue, keep in mind, this is the first issue. There are others. The first issue was when I was trying to pull the Docker image that I use for building and creating the LaTeX for the Doxygen documentation. For whatever reason, it was just not working. I don't really know exactly why it wasn't working. But it had something to do with, there was, I think, an update to the container between the last time I pushed a change and when I pushed this one. And for whatever reason, that update just, it was trying to look for something that it couldn't find, like during the build of the documentation process. I couldn't really figure it out. I tried messing with it for a while, then just said screw it, I'm just going to do it myself, and basically created my own container from scratch to do everything I wanted, and wouldn't you know it, everything started working again. So that was the first issue. The second issue was the Docker in Docker service that's used to deploy the Docker container in the next phase of the pipeline also wasn't working. I tried to figure out what the heck was going on. It was a very obscure issue, but it ended up being that I needed to specify the Docker driver environment variable and setting it to overlay 2. I don't know if that was actually necessary, but that was the only thing that managed to actually work. So once I added that to the config.toml file in the GitLab runner, everything just kind of started working again. Now, I'd make it sound like it was a very quick fix, but it took me a few hours to actually track down that this was the issue, because I was trying to, like everything in troubleshooting and debugging, I was trying to tweak a couple different things here and there, like seeing if this works, see if that works, see if this works. But then when you actually come across the solution, sometimes you still have like other lingering tests that you have lying around, so you're not actually sure what actually fixed it, if it was just one thing, if it was a combination of things. So then you kind of go through the process of eliminating things that you were trying to test until it stops working. You add the thing back, and then you can kind of narrow down what actually caused it to succeed. So that was how I figured out that it was the Docker driver, which, the thing that's weird is I never had to do this before, but again, it had been so long since I pushed to the pipeline that there almost certainly was changes in some other container or something somewhere that caused this to be a requirement, and I just missed it. And this is kind of what happens when you're on the bleeding edge, and why enterprises typically like to linger behind, because things like this happen where if you're on the bleeding edge, sometimes one day everything works just fine, you don't change anything, and the next day things don't work anymore. Now, technically, things did change. It just wasn't anything of my doing that changed. But yeah, this is why enterprises typically tend to stay on old versions for so long, because if it ain't broke, don't fix it. But then, of course, you get to the whole like, oh, yeah, this thing's actually going to be deprecated and it's not going to be supported anymore. Yeah, we should probably update now. And then they go through kind of the process of trying to figure out making sure everything works. And they do all of this behind the scenes before it actually gets pushed out to all of their developers. So it's more of a seamless transition. At least that's how it's supposed to go anyway. But we're still not done. We still had issues with the pipeline. So we fixed the issue of the Doxygen documentation not building. We fixed the issue of trying to get the Docker and Docker service to actually work. But then it came to actually trying to deploy the container to the server that I have, which hosts all my Docker containers, and that was failing. Thankfully, this was by far the quickest fix of them all, because I knew basically right away exactly what was going on. Remember a couple episodes ago where or maybe it was actually last episode, when I mentioned I was trying to add my new MacBook Air's SSH key to all of my servers, and I run it an automated script, and it accidentally nuked my access for my phone to one of my servers, and how I went around and hacked myself in order to get it working again. Well, that apparently was not the only victim of the great nuking of my SSH keys in my home lab. Also, as a casualty of the nuking, was my GitLab runner's SSH key in order to access my server that runs all my Docker containers, because that key was only in the Docker user and not in the generic Ansible user that I have on all the various servers in order to administer them, and which is what the script was using in order to ensure that the keys were in sync. So as a result, the GitLab runner's keys got nuked from the Docker server, and it was no longer authorized to log into it, pull the container, and deploy it. So that is why that particular stage of the pipeline was failing. But because I already knew what was going on, this was a pretty quick fix. Just go in, add the SSH key to the Docker server, update the key in the GitLab's, I forget what they call it, secure environment variables or something like that. And wouldn't you know it, did that, everything started working again. So I guess you can call me a plumber now, because I successfully unclogged and fixed all of these pipes. So who would have thought that software engineers are sometimes actually plumbers as well? But that was kind of the excitement of the nerdy things. But now we have to discuss the recommendation algorithms and why these computers aren't actually as smart as you think they are. Now, a lot of folks I find even today are still very shocked and sometimes creeped out when e commerce sites or social media sites recommend content to them, because sometimes it's like it can be very scarily accurate to what you were kind of thinking about, or what you were kind of wanting to buy, or whatever the case is. But the reality is, these recommendation algorithms don't need to know a single thing about what you're interested in order to actually recommend you something that would probably be a pretty good fit. And let's take e-commerce sites for example. Every item listed on an e-commerce site has what's known as a unique identifier associated with it. That way, that if it knows exactly which item you're looking at, and all this information's probably in a database somewhere, where it has, what the description is, how much it costs, who is the manufacturer, who's selling it, all that kind of information. And the e-commerce site has to be able to identify and discriminate all the items from one another, so each one has a unique identifier in order to distinguish it from another item. So even if you have two items of the exact same thing, so you have two identical MacBook Airs, but they're being sold by different sellers, they're going to have different item IDs, for instance. So with that being said, you can maybe start to see that the computer doesn't even have to know what this item is in order to recommend it to you, because as far as it's concerned, it's just a number. And this number, um, it could be anything from computer parts to camping gear. It doesn't really matter. As far as the algorithm and the computer is concerned, it is just solely a number. Now, for business reasons, uh, every e-commerce site is going to be tracking uh, basically everything about what gets purchased on their site, because they have to, give that information to the shareholders, say how much revenue we made, track what's selling good, what's not selling good, and all this kind of stuff. But as a result of that, you obviously, as a user of said e-commerce site, probably want to know what your purchase history is, so you can maybe remember what you bought, or you can go buy it again or whatever. So basically every e-commerce site also has a purchase history feature. So, okay, we know we're tracking who's buying the item, and we're also tracking what items individuals have bought. So you can maybe start to see how we can start to correlate these two things in order to provide recommendations. Now, if you're still not tracking it, here is an idea of potentially how these recommendation algorithms work. So first, let's say we have an item with the ID 12345. So we check, so say you either looked at or you purchased item 12345. What the algorithm can do is check, let's see who everyone else that bought item 12345, and with that list in hand of all the people that bought that item, let's see what other items they bought or other items they looked at. And then what we can do is we can start to count up and identify common items that were looked at or purchased by these individuals that also bought item 12345. And then what we're going to quickly start to see is there is a lot of item numbers that start recurring on a fairly regular basis. So we see, oh, hey, there's this other item, say, I don't know, 4567, that appears in 2,000 of these people's lists that also bought item 12345, whereas this item, say 8913, only appears 2 times. So that first item, it's probably has a lot higher chance of being something that you, a purchaser of item 12345, might be interested in, because others that bought 12345 also bought that item. So as you can see, we didn't even talk about what you're buying or what this item is, but we rationally came to the conclusion that this item is probably something you'll be interested in, because other people that bought an item you bought also bought this one. Now, it just so happens that in most instances, these items are going to be related. So, for example, like if you wanted to go buy, say, some camping gear and you bought a sleeping pad, there's a good chance that people that bought that sleeping pad also bought a sleeping bag for it. So, guess what? You're going to see a lot of recommendations for sleeping bags. It's not because, this algorithm is like knows everything about you. It's literally just comparing numbers of other people that bought a sleeping pad and sees, oh, people that buy a sleeping pad, or in the computer's case, that bought item number 12345, also bought these items as well. So let's give them to you as a recommendation. It has absolutely no idea what the heck it's referring you to. It just knows that it's frequently bought by others that bought the item you did. So you you don't even have to care if you're implementing one of these things, what these items are. You literally can just do some calculations to figure out what's common based on a similar item amongst, users. So this can apply, like I said, this applies to literally everything. It applies to camping gear, computer parts, beauty products, food items, literally everything. This same kind of formula applies. Now, Sure, sites can track other things as well. They can add weights to things for sponsored things and whatnot. But they also can do things like just because you didn't buy something, but because you looked at something, that could also be an indication that you might be interested in that product so that you can perform kind of the same check and find other items that people that looked at that item also looked at as recommendations. And you can see that this is all very deterministic programming, and there's absolutely no machine learning or AI buzzwords required in order to have a very smart and intelligent system to provide pretty accurate recommendations to you. Now, of course, it's going to be very data dependent, which is why the big, social media and e-commerce sites are so good at recommending things, because they have a very large data set to build off of. If you just have, a small online shop somewhere and you only have a few users on there, it's going to be a lot harder to provide good accurate recommendations because you don't have as much data to go off of and compare, where compared to some of the bigger e-commerce sites. So, social media is a little bit different, but also pretty similar. So, let's say, for example, that you interacted with post 4326. Well, out of all the other users that also were interested in that post, they also interacted with post 8761 and account EF765. So, and you can see how this kind of goes on and on. If you interacted with this post, and a lot of other people that interacted with that post also interacted with this other post and this user, there's probably a pretty good chance that you're going to be interested in those things as well. And here you go. Now, these algorithms also can take into account other things like weight. So, while it might also be kind of a fact that if you see a post from, say, a particular user, the chances that you're going to like their other post is probably pretty high. And honestly, if you're kind of going with this approach where you can compare, okay, if you looked at this, let's compare other people that looked at that and see what they also looked at, there's a good chance that there's going to be a lot of posts from the same user of the original post that kind of show up there, which is usually why you typically, if you start, looking at engaging with a certain user's content, you're going to get more and more of their content, because that's just kind of how it works. But this is also how these kind of bubbles start to appear. Now, also, I guess it also should be noted that just because these algorithms can do this, it's not to say that there also aren't like targeted recommendations as well, because you can also, I mean, at the end of the day, you're basically just creating a list of items to show the user. Now, depending on how you generate that list, you can have weights involved. So for instance, if there is a, say, big sponsored post that someone paid a buttload of money for, that you want to push to as many users as possible, you could add that give a very large weight to that post, and maybe some of the other posts that are more highly interacted with don't have as high of a weight. They kind of get pushed down and that sponsored one gets inserted. So, but at the end of the day, on the back end, these are just numbers. It's a company ID that paid to boost post ID, and it gives it an additional weight of X. You don't necessarily need to know who is promoting this content or what the content being promoted is from the algorithm's perspective. So, but this also, like I was mentioning, this kind of gets into where this idea of the bubbles come into play. Because how many times have you heard someone mention, oh, everybody's talking about XYZ, yet you have never heard of it? I've definitely had that happen on numerous occasions where, maybe I'll be watching a YouTube video, like a tech YouTuber or something. They're saying, yeah, everyone's talking about this on Twitter. And I'm like, I have absolutely no idea what you're talking about. Now, in fairness, I don't have Twitter or X, but still, I still have absolutely no idea what they're talking about. But this is kind of how these bubbles can tend to creep up, because if you interact with certain posts, the chance that similar posts to it other people are going to view, right? So because other people viewed those posts, there's a higher chance that you're going to view it because you viewed a post that they also viewed. And then this kind of spirals into the point where it's like a feedback loop where everyone's kind of, feeding off of one another. And this is kind of how these bubbles come up on social media. It's not any necessarily a malicious intent. It's just that you're interacting with this stuff, so we're going to feed you more stuff similar to this because there's a good chance that you're also going to interact with it. That's how these systems work, which is why I always find it hilarious when I'm, say, watching YouTube and I watch a video from one creator just one time, and then suddenly my recommended is flooded with videos from that same user, and I immediately can identify exactly what the algorithm's doing and be like, you're not getting me. Nice try, buddy. But this can apply to, like I said, similar to the e-commerce sites, it can apply to literally anything. It can apply to technology, it can apply to politics, and it can apply to cars. You name it, it applies to everything on social media. So, but again, I also want to reiterate the fact that just because this is a very simplified version, that's not to say these algorithms are actually that simple. There is a lot more going on behind the scenes because these recommendation algorithms aren't just pushing content that you might like, they're also pushing content that sponsors paid them to promote, so that has to get factored in. But then you can't push too much promoted content because then people aren't going to see things that they want to see. But you also can't not push the promoted content because that's what you're getting paid for. So you have to take in these weights into account, and that's kind of where kind of some of the complexity comes into place. But I wanted to give kind of a quick, very simple example of how this all works in action, because we kind of talked about it from an abstract, but this is going to kind of blow it way out and kind of just at the bare bones how like a recommendation algorithm would work. So let's say, for simplicity, you purchased item ID 1, and there is a list of, say, a few users that also purchased item ID 1. User A, user B, user C, user D, and user E. So in addition to buying item 1, user A also bought 5, 9, and 10. B also bought 9, 10, and 14. C also bought 5, 9, and 14. D bought 10 and 14. And E bought 5 and 10. So what you're probably going to notice is all of these people bought 1, which is why we mentioned them, but also there's a lot of similarities in other items that they purchased. There's a lot of 5s, a lot of 9s, a lot of 10s, and a lot of 14s. Now, not everyone bought 14, not everyone bought 5, not everyone bought 9, not everyone bought 10, but the fact is that all of these users that bought 1 also bought these items. So a very simple recommendation algorithm that you can do is you just count up these numbers, sort them by most common, sort them by the most occurring, put that first, and then kind of in descending order, and then you feed that back to your user of recommended suggested posts or items. And the chances are they're probably going to be pretty good suggestions because all these people interacted with an item that you already bought, and they also bought these things. So there's probably a pretty good chance that you're going to be interested in that. Now, again, we gave absolutely no background or anything to what these items are. It could literally be anything. Pick whatever you want it to be, right? Like, for instance, like if say you go to the grocery store, right? And you're trying to make, say, an apple pie. If you're trying to make an apple pie, and everyone else that's also trying to make an apple pie, there's probably going to be a lot of similarities that you're going to come across, right? There's going to be sugar, there's going to be flour, there's going to be apples. Basically all the ingredients that go into making an apple pie are going to be very almost identical. So you can start to maybe kind of correlate that. And you can also kind of abstract this too you can kind of take some history into it too. So you can say, oh, you bought items 1, 7, and 16. You can take each one of those numbers, lists of individuals that bought them find the lists of items that they bought and kind of make an even bigger list of recommendations to get an even more accurate representation of things that this person might like. So that's kind of a very abstract version of kind of understanding how these recommendation algorithms might work. But how would you actually go about implementing one from a kind of a design perspective? So here is kind of a another real world example. So let's say you are trying to build a computer, right? If you're building a computer, you're going to need a CPU, a motherboard, RAM, power supply, case, and a graphics card. Now, you might also get other peripherals too, but that's kind of the core components if you're going to be building a computer. Since everyone else building a computer is also going to be using and taking those parts, if you already bought a CPU, there's a very strong likelihood that you're going to get recommended compatible motherboards, RAM, cases, etc. because people that also bought that CPU were almost certainly also building a computer, and these are the components that they chose for their computer. So that's why they get recommended to you, because you both bought the same CPU and these are the kind of the builds they created. So you're probably going to be interested in the builds they created and the parts that make up that. So that's why you're going to be shown those. But again, at the end of the day, behind the scenes, these are all just numbers and IDs. But example would be like, if say there's some sponsor, some computer part sponsor that was paying for a sponsorship, you could throw in, say it's the item they're sponsoring is 1 2 3 4 5, right? If Even if 1 2 3 4 5 doesn't necessarily show up very high as a common item, you can weight how much the occurrence is with, say some external factor like a sponsorship value, and kind of combine those two together based on a weighting system in order to, weight the items in your list, right? Another thing that some sites will do is they'll put all the sponsored stuff at the top and then the actual results down below. You could do that as well. But you also kind of have to make sure that you don't push too much sponsored stuff, because then people just think all they're seeing is ads. But also, you don't want to, not push sponsored stuff, because that's kind of how you're making your money as well, through like sponsorship and ads as well. So you kind of have to find a balance. Now, the best sponsorships are the ones that are really good recommendations. A lot of people bought it, but also have a paid sponsorship for it. Those are obviously going to be the ones that rank really, really high, because they basically meet all the criteria for the weighting systems. So, but the weighting systems is kind of really where the complexity lies. It's not determining what you're probably going to like. It's determining, okay, now that I figured out what you like, how do I uh kind of marry that together with my business interests of making money and, appeasing my sponsors that pay for advertisement spots, in order to, still give you good content, but also, get people continuing to pay for these sponsorships. But again, all this is just numbers at the end of the day. So if you wanted to actually build your own recommendation system, it really depends on what your scale is, right? Because if you have too much data, that can be a problem, because it could take too long to process. But obviously, if you don't have enough data, then your recommendations won't be as good. So you have to kind of, depending on what your scale is, you could either have maybe a database somewhere, or you could divide your database based on geographic regions, or everything could be local in memory. It just kind of depends on what your scale is and how good you want your recommendations to be, how much compute you have, and all that kind of good stuff. But once you kind of figure that out, then you can kind of think of this as kind of a two table or two dictionary type solution, right? You have your table or your dictionary of all of your items, where the key would be the item ID, and then one of their fields that they have is all the users that purchased that item or interacted with that post. And then you have another table or another dictionary with the IDs being the user IDs, and then all the various items they purchased, interacted with, etc. So then what you can do is you can check, okay, user ID, interacts with item 1 2 3 4 5. Then you go to your dictionary or your table, pull out the list of users that also interacted with item 1, 2, 3, 4, 5, and you get that list of users. You then take that list of users, go into the users table or dictionary, pool all the lists of items that they interacted with, and then you can start doing the comparison and counting up all the items and sorting it from largest at the top, smallest at the bottom, and then you basically return that back to your front end or whatever of the item IDs to display to the user, and there you go. You just have a pretty darn good recommendation algorithm, and you have absolutely no idea what the user bought or what items you're recommending to them. But at the same time, your recommendations are probably going to be pretty dang good, assuming your data set is large enough. And the other nice thing about this too is because there's so much kind of processing going involved, a lot of this can be done in parallel. So if you have you're checking a single item, that item probably has a fairly large list of users. So you can put that list of users into a queue, have kind of like a thread pool or some kind of distributed computing system set up in order to kind of take each user off the queue, kind of pull their list from the table, and then you have some centralized list of the items that you're counting for. Now, of course, you're going to have to make sure you avoid race conditions and all that stuff, but you can perform all of these lists and kind of calculate them all in parallel, which is very, very nice because the items that user A interacts with is not dependent on the items that user B interacts with, so you can execute them at the same time. So very good from a kind of an optimization perspective. There's a lot of ways that you can optimize this to make it pretty dang quick. And also give pretty good results as well. But again, you don't even have to know what your users are buying, interacting with, or what you're recommending them, and you can still give really, really, really good recommendations based on just comparing other people that bought or interacted with that item with other items or things that they interacted with, and you can make a very powerful recommendation system without knowing anything. So I hope that this kind of helped peel back some of the mystery of these recommendation systems and kind of maybe helped you understand that, yeah, these things actually aren't maybe necessarily as smart as I thought they were, or maybe me explaining this and kind of all the logic that goes into kind of determining this makes you think, wow, these are even smarter than I thought they were. But at least, hopefully, regardless of which camp you fall into, you at least have a better understanding of how these systems work. So the mystery of them just giving you something that you happen to like is kind of removed, and you can kind of maybe understand of how it came to this decision of giving me the recommendations that it did. So before we wrap up for this week's episode, we do have to finish up with our trivia question for the week, which is Elaine Rich is credited with creating the first recommendation system called Grundy. What year was Grundy created? And again, the hint there is whatever year you were initially thinking, it's probably earlier than that. So if you said 1979, congratulations, you got this week's trivia question correct. And if you enjoyed this episode, I ask that you leave it a rating and review and subscribe to the Dark Assassins podcast if you haven't done so already. And be sure to share with a friend or family member. I think we covered a lot of good stuff, from the first AI cyber attack, if you will, to how recommendation algorithms actually work. And if you have any questions about this week's episode, or if you have any comments, topics, or ideas for future episodes, you can leave a comment down below if you're on YouTube, or you can shoot me an email at contact@darkassassinsinc.com. The link for that is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.